In this video, we're going to learn about the conjugate root theorem. The conjugate root theorem is in two parts. One's talking about radicals and one talking about complex numbers. So if a polynomial with rational coefficients, meaning that none of the coefficients in front of x squared or x has a radical or an imaginary number, then the irrational roots of that polynomial that have the form a plus the square root of b, meaning they have a square root involved, occur in conjugate pairs. That is, if a plus the square root of b is a root, then a minus the square root of b is a root. And that's also saying that a and b are rational as well. There's not a square root within a square root. So the reason why this works is if you multiply a number of that form by its conjugate. So in this case, if I say that 2 minus the square root of 3 is a root, then 2 plus the square root of 3 is a root, leading to the polynomial having the two factors x minus 2 minus the square root of 3 and x minus 2 plus the square root of 3. So having those two solutions. But the reason why we say this is true is if I multiply these conjugates together, 2 times 2 is 4. 2 times the square root of 3 is 2 square roots of 3. Negative square root of 3 times 2 is negative 2 square roots of 3. And then negative square root of 3 times square root of 3, the square roots cancel, giving me 3. Or square root of 9, but that will simplify to 3. And now I'll see here that these two middle terms cancel with the square roots. And I have 4 minus 3, which is 1. So multiplying by the conjugate of that square root term got rid of the square roots. So that's why we end up with a polynomial with rational coefficients. So that means if I were to multiply these two factors together, my polynomial would only have rational coefficients because it won't have a square root in it anymore. So let's see how that works. So again, x times x is x squared. X times negative 2 square roots of 3 would give me, multiplying the x in, negative 2x, and then minus square root of 3x when I multiply it in, and then negative 2 minus square root of 3 times x would be negative 2 times x, which is negative 2x. And then negative is a positive square root of 3, so then plus 3 square root of 3x. And then these two numbers multiply together. I just did at the side. That just gives me 1, so I can put a plus 1 over here. And it is a negative times a negative, but that makes a positive. So now, if I combine my like terms, again, just like over here, my square roots cancel, they cancel again over here, leaving me with x squared minus 4x plus 1. So it's really nice how that happens, that this is a polynomial with rational coefficients. You say there's no radicals in it. But its roots are in conjugate pairs. It also works with imaginary numbers as well. So I'm going to put that in a little bubble to show you how that works. But let's look at these imaginary numbers. So let's say we have negative 2 plus 5i is one root. Well, then another possible root, or the other root, not possible, but the actual other root of that polynomial would be negative 2 minus 5i. Again, they appear in conjugate pairs, meaning so a plus bi is a root, then a minus bi is a root as well. So if I were to write that polynomial, it would look something like this. P of x is equal to x minus the left root, so negative 2 plus 5i, and x minus the other root, negative 2 minus 5i. Simply. But you see here, if I multiply by complex conjugates, we have negative 2 times negative 2, which is 4. Negative 2 times negative 5i is plus 10i. 5i plus times negative 2 is minus 10i. And 5i times negative 5i is minus 25i squared. You'll see the i's cancel in the middle, but there's still an i left. But luckily, we remember that I squared is equal to negative 1. So that becomes negative 25 times negative 1. So that's 4 plus 25. So over here, we had that 4 minus 3 happen up top. But here we have 4 plus 25, which is 29. So you'll see here that we end up with a real number when we use the complex conjugate. And that same thing should happen as factors, just like we saw up top. If I multiply these together, p of x would equal x times x, which is x squared, and then x times negative of negative 2 minus 5i. So that negative distributes and end up with plus 2x plus 5ix. I'm going to multiply this by x. And over here, I can distribute that negative again. So I get 2 minus 5i times x. So that's plus 2x minus 5ix. And lastly, when I multiply these together, that gives me 29, just like you saw on the left. And again, those I terms cancel, and I'm no longer left with any imaginary coefficients. They're all real. So I have x squared plus 4x plus 29. So that's why we have a guarantee that they come in conjugate pairs. So let's put this into practice. So we're going to write a polynomial function, just like I did here, with rational coefficients, so that p of x equals 0 has these given roots. So if I want rational coefficients, which also falls under the real category, then I need to think about the conjugate pairs of radicals, square root radical answers, and imaginary answers. So here, if I have given square root of 2 as a root and 1 plus I as a root, since I know it has rational coefficients, my additional roots would be negative square root of 2, which in this case, a would have been 0 square root of 2, so then it's like 0 minus the square root of 2. And my other additional root, instead of 1 plus I, my other one would be 1 minus I. And I can go ahead and write out my polynomial. P of x is equal to x minus the square root of 2 times x minus negative square root of 2, which would just be x plus the square root of 2, times x minus 1 plus I times x minus 1 minus I. And now I can multiply these out to get a polynomial with rational coefficients. So x minus the square root of 2 times x plus the square root of 2. This is a conjugate pair, but multiplying that out, I get x squared, and then I get positive square root of 2x and negative square root of 2x, which will cancel, leave me with minus negative, that negative times a positive, 2. On the right, when I multiply these out, I get x times x, which is x squared, and then x times, distribute the negative, negative 1 plus I, so it'll be negative x plus ix, and then distribute this negative, negative 1 minus I times x, which would be negative x minus ix, and then 1 negative times a negative is positive, but 1 plus I times 1 minus I. This is a conjugate pair, so I could use that difference of squares to multiply them, giving me plus 1 squared minus I squared to get that last bit. So I can use the difference of squares to multiply them since I know they're conjugates. The middle term should cancel. Then simplifying all of that, I end up with x squared minus 2 times x squared. Negative x minus x is minus 2x. The ix and the negative ix cancel, just like I expected it to. And then I have 1 squared minus I squared. Since I squared is negative 1, that's 1 minus negative 1, giving me 1 plus 1, which would be 2. And now I can multiply these together to get my final answer. Distribute in the x squared minus 2, and I get x squared times x squared minus 2 minus 2x times x squared minus 2 plus 2 times x squared minus 2. So x squared times x squared is x to the 4th. X squared times negative 2 is negative 2x squared. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 2 is plus 4x. 2 times x squared is plus 2x squared. And 2 times negative 2 is negative 4, giving me x to the 4th minus 2x to the 3rd. And then negative 2x squared plus 2x squared cancels. And then I end up with plus 4x plus 4, or minus 4. as my polynomial. Let's try this again with another problem. So we'll have 2 minus 3i, 8 and 2. Now 8 and 2 are already real numbers that aren't irrational, so they don't need additional roots. The only one I need to consider is, since I have 2 minus 3i and they are rational coefficients, I need to also consider 2 plus 3i. That's my additional root. So when I go to write my polynomial, I have p of x is equal to x minus 2 minus 3i, x minus 2 plus 3i, times x minus 8 and x minus 2. Now I'm going to take this multiplication a little bit slower than I have previously, just to definitely show you every step. So first times first, so x times x is x squared. Then x times negative 2 plus 3i. So I'm just going to put minus 2 plus 3i x, so you can see them multiplied together. And then minus 2 minus 3i x. And then my last will be plus 2 minus 3i times 2 plus 3i. And then all that's going to be times x minus 8 times x minus 2, which would be x squared minus 2x minus 8x plus 16. Now I'm going to simplify all of this mess I just wrote down here. So I have x squared to start. Then I have negative 2x minus 2x, which is minus 4x. Then negative 3ix, then minus negative 3ix, so it's plus 3ix, so those would cancel again. And then I have 2 minus 3i times 2 plus 3i, which those middle terms will cancel, just like you saw over here. But we'll have 2 times 2, which is 4. And then negative 3i times 3i, which is minus 9i squared, which will end up being plus 9 later when I change the I squared. Again, those middle terms, negative 6i and positive 6i, will cancel. That's why I don't write them. And on the right, I have x squared minus 10x plus 16. So now I need to multiply x squared minus 4x, then 4 plus 9 is 13, times x squared minus 10x plus 16. So I'm going to distribute. That would give me this x squared on the right times x squared minus 4x plus 13 minus 10x times x squared minus 4x plus 13 plus 16 times x squared minus 4x plus 13. And then all together, that's going to give me x to the fourth, which will be the only x to the fourth I'll get. Then negative 4x cubed. And I'll also get a negative 10x cubed. So if I were to write out all these terms, I'm going to do it in this little bubble up here. So I have the space for my answer. But I have x to the fourth minus 4x cubed plus 13x squared. And then I have minus 10x cubed plus 40x squared. And then minus 130x. And then plus 16x squared minus 64x. And then 16 times 13, which I'm going to use a calculator for just to be safe. 16 times 13 is 208. So my final answer will be x to the fourth. Then my 2x cubed will be minus 14x cubed. And I have 13x squared, 40x squared, and 16x squared. So 13 plus 40 plus 16 gives me plus 69x squared. Now I'm going to finish it off on the bottom row, but I have negative 130x minus 64x give me minus 194x, and then plus 208 for that polynomial. And for the last one, I have 4 plus square root of 5 and 2i. So again, this is a rational, and this is a complex. So I'm going to use their conjugate pairs to help me find additional roots first, which would be 4 minus the square root of 5 and negative 2i. If there's no coefficient in front of it, the a would typically be the real part, but there's no real part, so it's just plus or minus 2i would be the two imaginary roots. So to write this polynomial out, I'll have p of x is equal to x minus 4 minus the square root of plus the square root of 5 times x minus 4 minus the square root of 5, and then x minus 2i and x minus negative 2i, which is really just x plus 2i. So multiplying that one out, I'll get x times x, which is x squared, x times negative 4 minus square root of 5, which would be negative 4 plus the square root of 5, so minus 4x plus square root of 5x, and then negative 4 minus the square root of 5 when it's true of that negative times x, so it's minus 4x again, but minus the square root of 5x, and then negative 4 plus square root of 5 times negative 4 minus the square root of 5, the negatives cancel, and these are a conjugate pair, so I'll get 4 squared, which is 16, minus square root of 5 squared, which is 5. And on the right here, this is also a conjugate pair, so I'll get x squared minus 2i times 2i, so 4i squared. Bringing me to my next step, simplifying x squared. Then we have minus 4x, which is minus 8x. The square root of 5x's cancel. And then I'm left with 16 minus 5, which is 11. And then I have x squared. And since I squared is negative 1, this is now plus 4 instead of minus 4i squared. And then I can distribute that into the parentheses, and I get this x squared times x squared plus 4. Negative 8x times x squared plus 4, and then plus 11 times x squared plus 4. Distributing there, I get x to the 4th plus 4x squared minus 8x cubed minus 32x, and then plus 11x squared plus 44, which gives me my polynomial with rational coefficients to be x to the 4th minus 8x cubed, and then I have 4x squared and 11x squared, so that's plus 15x squared. And then minus 32x, then plus 44. So it's a very clever way to make sure you find all the roots and get a polynomial with rational coefficients. They'll always come in those conjugate pairs. And if you want further proof as to why, if you just look at your quadratic formula, negative v plus or minus the square root of b squared minus 4ac. That plus or minus leads to that conjugate pair, because you can also write the quadratic formula as negative b over 2a plus or minus conjugate pair the square root of b squared minus 4ac over 2a. And again, that radical, if it stays there, leads to like a 2 plus or minus the square root of 3, which is where that comes from. And if it's negative on the inside of that radical, then it's going to be a complex number, and again, it's going to be plus or minus. That's really where those come from. Whenever you think of those quadratic factors, ax squared plus bx plus c equals 0, they'll always come in conjugate pair solutions. And that is how you use the conjugate root theorem.